to use it to solve real-world problems and help make the most out of the methods that we could use. Specifically, we worked on a Udacity project that included simulating the programming of the calculations that we had to do in order to rescue the astronauts from the Apollo 13 mission.
We used the sine and cosine functions traditionally used for trigonometry, but also useful if you're trying to plot orbits of spacecraft or planets or moons. And we used those to code in the basics for later projects.
Subsequently, we learned about a technique used in solving differential equations called the forward-Euler method. We plotted two graphs that show the changes that take place in position and velocity when an object falls down the hole going towards the center of the Earth. As you can see on this graph here, the height decreases at an increasing rate because the velocity increases as the object falls due to the acceleration of gravity, as you can see on this graph here.
After learning how to code an acceleration formula, we learned how to plot the trajectory of the moon considering a circular orbit rather than an elliptical one as it would be in real life.
We used Newton's formula regarding gravitation between two masses there, which helped us later on in achieving accurate results. Then, in order to understand a bit better how we would plot the trajectory of the spacecraft, not just the moon, we investigated how separate particles would move when they're launched at different angles. So here we have trajectories of particles launched from angles ranging between 20 and 70 degrees. For this, we again use the forward-Euler method, which includes taking small time steps, which we call h, and finding out the next positions and velocities using the previous ones. Of course, we initialize the initial positions and velocities as well as g, which is what helps us achieve the gradient correctly.
Using the acceleration function, which was already coded, we're able to plot the trajectory of a spacecraft in elliptical orbit using the forward-Euler method. As you can see, the inaccuracy of the method shows that the ends of the ellipse don't perfectly meet up, which meant that we needed to code in a different method.
There, as Bart said before, this forward-Euler method, although seemingly it works out pretty well, it has a lot of errors if you increase the step size and generally use it on a larger scale. So on this graph you can see that as the step size increases, the error explodes, which could be very dangerous for astronauts that are like in space in reality.
We need to use a more accurate method to account for the errors in Euler's method, as seen in green on this graph. Another method used is Hughes' method, which effectively uses Euler's method to calculate an average. As you can see, this cancels out the majority of the error in Euler's method.
Yeah, so this is Hughes' method and this is Euler's method. Notice how large the difference between the errors is, even at a huge step size. Then we encountered more problems. Another problem was that we were unable to generate the ideal step size for every position in the orbit. Obviously, because the step size might need to be altered when we come closer to the Earth, as the force acting upon the spacecraft from the Earth is larger. The error, if we use the larger step size, would basically skyrocket the spacecraft out of orbit and into outer space, which we definitely do not want. So on the plot here, we use the adaptive step size in order to generate a more accurate trajectory and a more accurate way of presenting how we would need to calculate the trajectory. So here, as you can see, the step size decreases as we get closer to the Earth in order to assure that our orbit does not...
You just want to explain what the step size actually is? So what each point is?
Okay, so basically each point is the calculation. We calculate using the previous point, the next point. So here we calculate more points in a given amount of time in order to plot the positions and the velocities using the forward-Euler method more accurately. So yeah, we don't want the spacecraft going into outer space.
We were able to use the law of conservation of energy to show the fluctuation in energy throughout the orbit. Although it looks like energy isn't being conserved in this graph, you can see due to the repetition of the pattern, we can say that overall it is conserved, although not accurately.
Yeah, also you can see that the fluctuation is very small, and this difference in joules is like inconsequential when we're dealing with such large numbers. And you can see that because of the repeating pattern, each point in the orbit has the same energy levels. Then, obviously, in order to save our astronauts, we would need to help them realize how to use the boosters in their spacecraft to fire them back to Earth. So we simulated how the boosters would work in order to understand how to use them in order to get the right trajectory. So here, you can see that if we use the booster at that red point there, the trajectory alters, and even though it gets almost to the correct trajectory in the end, there's quite a big error there. So we would need to investigate at which point the boosters need to be fired in order so that we don't get a very big error.
The simulation here that we made of a different point boosting, that's the ribbed up there where we boost, shows us that if we boost closer to the Earth, the effect of the boost is much larger. So as you can see, the error between here and here is far larger than it was in the previous slide because we've shifted the position of the boost from here to here.
Yeah, so that would obviously slingshot the spacecraft way over there, which we do not want. So finally, the goal of our mission was to rescue the astronauts that went on the Apollo 13 mission. For this, we would use the different functions that we used before to predict the trajectory of the moon and the spacecraft, of the spacecraft, and how the moon and the Earth would affect it. We also used the different values for boost in order to figure out, like shown before, which would be the ideal one in order to get them safely back to Earth and not slingshot back into space or crash into the Earth.
Right. Can I just jump in for a second?
Yeah.
So basically, in summary, what these two people have done here is taken brand new mathematics, because differential equations haven't really been introduced to their course yet. They've been able to take all of this on board and able to program the path of the moon around the Earth, the path of a spaceship going around in space, how the moon's gravity affects the spaceship, how the Earth's gravity affects the spaceship, how boosters affect the trajectory of a spaceship if you change the speed at a given time, and how to do that so accurately that you can navigate the spaceship and make it safely land back on Earth. And doing all of this with basically the maths behind all of this they had never seen before. So they had to pick up these skills and then not only learn the maths, but learn how to code that in 2 weeks, which is pretty impressive, I think.
Thank you.
Very good.
We're not
Very good.
sorry.